Good evening, one and all. Let me have the discussion on metaheuristic algorithms and their applications in science and engineering. We'll take a few applications in engineering as well as science. Three applications I'll discuss today on engineering part, and one mathematical problem I'll discuss in my presentation. So myself, Dr. Shovik Ganguly, I am an assistant professor serving in the Department of Electrical and Instrumentation Engineering at Thapar Institute of Engineering and Technology, Patiala, Punjab, and I am from India as well. So welcome you all to my presentation on this new coinage of metaheuristic algorithms. This is my brief background. I'll also not go through it too much on it because most of my students are aware of it. So I did my BTech in electrical engineering, did my master's in mechatronics, and my PhD in system identification and control. So coming to the coinage of the terms, we will first of all discuss about heuristic and metaheuristic, discuss about the brief history of metaheuristic algorithms, how it came into being, and after that we will take up the need of hybridization or combination of metaheuristic algorithms, and over here we are to take up some of the hybrid techniques which we have developed, and in the process we will discuss about some of the applications of these hybrid heuristic algorithms. So first of all, let us define heuristics. Heuristics usually mean something to find by trial and error. So there is no mathematical proof for the heuristic. Meta as a term implies it means beyond or higher level heuristics. So metaheuristics are considered to be superior as compared to the heuristic algorithms. However, there is no differentiation or agreed differentiation between heuristics and metaheuristics, and both of them are used almost interchangeably. However, we find that a randomization is the key associated with the most of the heuristic techniques. Coming to the features of the metaheuristic algorithms, I'll specify two features primarily by virtue of which we can work with any metaheuristic algorithms, or which we consider as two major components of the heuristic algorithms. They are mainly the exploration and the exploitation. So let us define one by one what you understand by exploration and what we understand by exploitation. So exploration basically means finding out a diverse solution in the entire solution space, whereas exploitation means focusing on a particular region or a local region, and based on some current good solution in that particular region. We need a proper balance between the two, almost 50-50 portions we engage for the metaheuristic algorithms, 50% for the exploration and 50% for the exploitation. Coming to the brief history of the metaheuristic algorithms, it started way back in during World War II, where Alan Turing was apparently the first person to coin this term heuristic search, or he used the heuristic search method during World War II. No further developments till 60s and 70s saw the development of or evolvement of this genetic algorithm, and in the 80s you come across this simulated annealing technique, and then in 1992 and 95 there were some progress with respect to ant colony optimization and particle swarm optimization. Particle swarm optimization is one of the most cited papers as of now. And in the year 1996 or in 97 later on, and we found the development of differential evolution. So these few algorithms were developed from 60s to 90s, and then with the advent of this 21st century, uh, we find that many algorithms started developing, or people have started working on the nature inspired algorithms or the metaheuristic algorithms, and every now and then they are coming up with a solution of some of the fascinating algorithms in the form of artificial bee colony optimization, firefly algorithm, cuckoo search algorithm, bat algorithm. These are only to name a few, and many of them have evolved, and they are still in the process of evolvement. So let us first of all discuss about bacterial foraging algorithm. The bacterial foraging algorithm was basically coined by Passino, who was working on the E. coli bacteria that reside in our intestine. So basically foraging is a habit of the animals to search for, to manage, or to consume their food. Their bacteria usually give up two type of chemicals, either the attracting or the repelling chemicals into their neighboring atmosphere to move towards a food source or move away from it. So you may find in the figure that there are two movements I have shown. One is the counterclockwise rotation of the flagella of this bacteria, which we call as the swim movement, and the clockwise rotation of the flagella, which we refer as the tumbling of it. So they either swim or they tumble, and in the process they are attracting, or they generate some chemicals into their neighboring atmosphere to move towards a food source or to move away from it. And usually it consists of four different steps, namely chemotactics, swarming, reproduction of course, and elimination and dispersal. But when we find that bacterial foraging, it has uses a lot of user-defined parameters, and when we are using a lot of user-defined parameters, it is obvious that its performance will decrease, and it will be depending upon the choice of these user-defined parameters. They are not fixed parameters, they are chosen within a particular range, and so that if we use these user-defined parameters or more of these user-defined parameters, it is less likely to give very good performance. And its complexity will also with the dimensional complexity and with the problem complexity, it fails to achieve some, or fails to give up, or fails to yield some good results. Okay. Coming to the next algorithm that we are on the discussion, that is a firefly algorithm. This is typically motivated by the communication behavior and the flashing pattern of the fireflies, which are usually available in the tropical environment. So there are two aspects that we usually come across. One is the variation of the light intensity, and the other is the formulation of attractiveness. So attractiveness is usually determined by the brightness or the light intensity, which in turn will be related to your objective function, which we need to optimize. Finally, this algorithm, we will say that it has shown very good promise, and it is far more superior as compared to several other algorithms available in the recent past, and that's why more and more of their variants and their hybridizations have been carried out using firefly algorithm. So as the light intensity diminishes and with the increase of the distance from the source, usually the light is absorbed in the media, and there is an absorption parameter also. There are in fact three parameters to deal with: alpha, beta, and gamma. These are the three parameters which are user defined, relatively less than as compared to the user defined parameters of the bacterial foraging algorithm. Coming to the next algorithm, we have the flower pollination algorithm. This is inspired by the pollination process of these flowering insects, flowering plants. And there are two fundamental steps in this flower pollination algorithm. One is a global pollination technique, and the other is a local pollination technique. In the global step, what happens? Your pollens are carried usually by the insects. So if they are carried by the insects, naturally they can travel a considerable distance. Whereas local pollination, it is usually available within a close vicinity or within a particular place. And who should determine the shift between the local and the global pollination? It's the switch probability, which we usually define by the term P, and this is usually employed to shift between the global pollination and the local pollination. And we have several formulations available in the literature of this particular switch probability. An adaptive variation of this particular switch probability leads to improved performance of the solutions for different optimization problems. So this is another important technique or another important metaheuristic algorithms which have been used almost extensively. This is perhaps the most popular amongst the researchers, and it has reached almost in each and every field of engineering and science, be it civil engineering, be it electrical engineering, be it mechanical engineering. Gray Wolf optimizer is almost everywhere. So this is basically an algorithm that usually simulates your leadership hierarchy and the hunting mechanism of the gray wolves. Gray wolves are usually available in the northern part of America, and they usually move in groups of 5 to 12 members, and they usually maintain a very strict social hierarchy. And as you may find that the pyramid on the right hand side, where alpha, beta, delta and omega are the different types of wolves available to us. So alpha is the leader, of course, and beta, delta and omega should follow the orders led by alpha. So alpha is a leader in the prey hunting process, and they normally hunt by encircling the prey, and when they complete the hunting, when they complete the hunting process, when the prey stops moving. So one of the most popular cited metaheuristic algorithms as of today. Now when we are talking about some of the metaheuristic algorithms which we have taken up in the discussion, we have also come up with this idea that there are some drawbacks definitely of the pure techniques. Your pure algorithms or your single algorithm cannot always deliver an optimal solution, first of all within an acceptable time frame, and also cannot deliver the quality of solutions that we may expect, and thus they are inferior to the hybridized algorithms. So hybridization has thus become an fundamental feature of some of the high performing algorithms. So over here we have we'll be discussing about Talby's taxonomy for the hybrid metaheuristic algorithms, according to which the two algorithms can be hybridized either in high level or in low level, and with relay or co-evolutionary approach, and they may be either heterogeneous or homogeneous. So let us discuss one by one what are these features all about. So as you may find over here, I have used one algorithm after another. So algorithm 1 is my first one, and second algorithm is being denoted by algorithm 2. So one is used after the another. So that means it's a relay type hybrid that we are talking about according to Talby's taxonomy. Another thing is that we have mostly used the functionalities we have kept the functionalities of the algorithms intact so that we can call it a low level hybrid. And third important thing, two different algorithms we have used in our analysis. So it is a heterogeneous type of algorithm. Okay, so this is about the algorithms. We come to the hybrid algorithms later on, but before that, what is the methodology which we have started with? We have taken a dimension of 100 being considered for the minimization of two types of test functions, namely the unimodal and the multimodal test functions. So the unimodal test functions are usually used as a measure for the exploitation feature of the algorithm, and the multimodal test functions are normally used to measure the exploration capabilities of the algorithm. Population size we have assumed as 30. This is as per standard literature, and maximum iteration we have kept as 500. This is also well acceptable in the literature. We have used 20 independent test runs for carrying out the statistical measures of the test system. And why is it so? Because these are stochastic algorithms and they do not give rise to the same solution every time they are being run on a system. Once again, we have carried out the Wilcoxon rank sum test 2. This is basically required as a non-parametric test. This is one of the non-parametric tests. There are several available in the literature, and this is one of the non-parametric tests that we are going to take up here in order to validate that the results are significant. So this is basically a non-parametric test that we perform after the results have been evaluated. And finally, getting to the unimodal test functions that we have the 5 test functions have been considered. They are having separate names. I'm not going to the mathematical discussion, but at this point of time, that we need to have the minimum value of all these optimized functions to be closing to 0. And their search domain and their dimension I have already specified in the previous slide. So the dimension is already being provided. We have considered the standard search domain of each of these individual functions, and we are trying to optimize it, and we try to prove that these results are close to 0. Let us see what happens. There are some more. These are some of the multimodal test functions. These are well accepted in the literature, and you'll find everywhere these type of literature available, and this type of test functions available, and you can consult any textbook also, because these are already available in the textbooks even. So these are some of the multimodal functions that we are going to test, and previously we had considered 5 unimodal test functions as well. Coming to the discussion of the results, as you may see that there are 5 proposed techniques which we have used. First one is the combination of the Firefly algorithm with the bacterial foraging algorithm. The second one is the combination of the Firefly algorithm with the flower pollination algorithm that we discussed just now. The third one is a combination of pattern search with Firefly algorithm. Usually pattern search is a very good algorithm for performing the exploitation part. That's why it is being employed or combined with Firefly technique in order to develop a hybrid algorithm. The fourth one is your combination of gray wolf optimizer and Firefly technique. The fifth one, or the last one, this is a combination of chaotic Firefly algorithm with gray wolf optimizer. So you may see that I have compared almost more than 15 or 20 algorithms, around 20 algorithms nearly being compared with 5 of these hybrid techniques. And if you look at the results, you'll find that mostly the hybrid algorithms are performing better than the standard heuristic techniques, or some of the latest heuristic techniques being compared. Uh, of course, for this particular test function, you may find that GWO-CFA is performing better as compared to any other algorithms. But if you look closely at the other techniques, these are some of the results that we interpret, and these are quite popular in the literature, finding out the best value, finding out the worst value, or reporting the worst value, the average value, and standard deviation as well. The standard deviation is usually a part associated with defining the stability of the algorithm. More close is its value towards 0, or less is the value of the standard deviation, better is the stability of the algorithm. So similar test functions can also be taken up, and we have analyzed the results of this test function F2, and here also we find that the bulleted results of GWO-CFA is outperforming any other algorithms with which they are being compared. This is also available for the test function F3. I'll skip quickly. These are some of the results in which the bird swarm optimization, or bird swarm algorithm rather, BSA, is almost equaling the results of 2 of the hybrid techniques, or 2 of our proposed techniques. F9, this is of course the multimodal test function that we had defined earlier, and this is a part where we find that FFPS is performing better as compared to the other algorithms under consideration. And in F10 also we find that once again FFPS algorithm is performing better. So mostly we have the better results of FFPS and GWO-CFA or FAGWO likewise. So these are all about the test functions. Let's move on to the Wilcoxon rank sum test results, where the p-values are reported over here against the algorithms being compared, and you will find that there are only a few values reported. Most of the values are less than 0.05, which we have taken as the confidence interval. If the results are less than 0.05, the results will be assumed as significant results, and if they are greater than 0.05, they will be considered as invalid or insignificant results. So this is part 1 of these results, and here we have part 2 as well. So mostly you'll find that the algorithms have performed. You may find that this is the only part which is an insignificant, which is shown by the help of an underline. This is not a number, and these type of algorithms, mostly we find that they are performing or outperforming the results. Coming to the discussion of the convergence characteristics, we have also found out the convergence characteristics, and you may find from the figure it's quite clear that my hybrid algorithms are performing better as compared to the parent techniques, as well as some of the techniques with which there has been some comparison carried out. Coming to the process of system identification, this is a process usually employed for the analysis of a dynamic system. A model structure is normally selected in the conventional technique, and the unknown parameters, they are being calculated by the minimization of an objective. And this process usually will require a large set of input output data for the system, which for example, if the system does not have the availability of the data, this particular method, which we are calling as a conventional technique, will fail to operate. So what we do, there are 2 types of models which we have selected. One is referred to as a Hammerstein model. The Hammerstein model is usually the model in which your linear systems with static linearities or the static non-linearities are connected to the input side, and this is the model being taken into account. My input is denoted by UK, and the white noise is being represented with the help of WK, and yk is denoting the output of the system. So we have a system where if the static nonlinearity or any chosen nonlinearity is taken at the input side of the dynamic system, then it is considered as the Hammerstein model. If we have the Wiener model, then definitely your static nonlinearity is at the output side. So just the shifting of positions of the static nonlinearity block will have an impact of determining which type of model which we are considering for identifying or parameter estimation of the system. So this is a basic flow diagram that we have taken. The input signal which we have taken is usually pseudo-random binary sequence which is not a biased signal, and we have contaminated, or we have polluted the system with polluted the input with a white Gaussian noise having a signal to noise ratio of 50 dB, and if over here on the left hand side is denoting the static nonlinearity being considered, this is the actual model and this is the estimated model, and we take a difference and finally use the objective function which we have considered for this case, the mean square error. And when we consider the mean square error, we are able to achieve better results. Let's see the results. If before that I'll go through the methodology once. And sample size of the input has been considered, which is taken as 2 to the power n minus 1, and it is considered to be 255 in this case. And we have, as I told you earlier also, the input signal has been contaminated with white Gaussian noise, and having a fixed signal to noise ratio. This can be altered, of course, and in this particular problems for optimizing or finding out the estimates of the parameters, we have used a population size of the Metaheuristic algorithm as 20, and a maximum iteration of 100 has been considered for each of these experiments. And finally, 20 independent runs have been carried out once again in order to get statistical measures of the test system, and we have also performed the Wilcoxon test over here, although I have not shown it in my slides. So the next one is some of the results that you may find. I'm not defined the test system, I'm showing you just only the results, and in the results you may find that these are some of the parameters of the model B0, B1, A1, A2, A3, A4. These are some of the parameters of the model which we have considered, and those are the having some fixed values, and how much close we have estimated is being shown here. And C1, C2, and C3 are definitely denoting this thing, the static nonlinearity parameters. So what we are estimating at, we are trying to get close to these values of the parameters. So this is a Wiener system which we have considered. Delta operator approach is being followed over here, which is a unification of discrete time systems with that of the continuous time system. So we have tried to unify the domain of analysis as well. So some discussions on the actual and the estimated parameters of the Hammerstein model as well. And here also we find that your hybrid algorithm is providing a very closed value, close to this original parameters of the model, as well as the static linearity coefficients. C1 and C2 are the non-linearity coefficients. So we have incorporated over here the non-linearities. We have injected a white Gaussian noise having a certain signal to noise ratio to make our system more robust, or to make our parameter estimation process a little more robust. So coming to another important application in engineering is a model order reduction approach, which is usually carried out for modeling or analyzing or designing or implementation of some large scale system, and we need to diminish it, and we have extensive applications of this in computational physics, in MEMS devices, in some chemical processes. Now, a reduction of large-scale systems have been explored over several decades, and there were several methods which have been popular, and they are popular either in time domain or as well as in frequency domain. So recently, meta-heuristic algorithms are being used for the model order reduction. I am not the first person to propose it. So there are already people who have come up with some excellent ideas regarding estimation, and either these are in combination with the classical techniques, and they are mostly used in the continuous and the discrete time systems. And the essence is to minimize certain error index, and by virtue of which we will obtain the parameters of the reduced model by this error index, which is usually obtained by the step response of the higher order and the reduced order systems which we are proposing. So coming to the challenges associated with model reduction technique with only the metaheuristic approaches. Previously, there were classical techniques being used to solve the denominator polynomial, and the numerator coefficients are being obtained using the metaheuristic approaches. So first of all, there is a matching of DC gain that is being required. We require to preserve our stability. We need to retain the minimum phase or the non-minimum phase, whether there are any poles on the there are any zeros on the right half of the S-plane or not, that we are going to determine, and also preserving your time and frequency domain parameters, which we usually have rise time, settling time, overshoot, all these parameters, or some frequency domain parameters like gain margin and phase margin. So this will be appropriately addressed or associated in deciding the cost function and in deciding the constraints as well. These are normally the constraints that we used. So these are some of the test systems. I'll simply just have an overview of the test system. The first one is a continuous time system, which is usually a single input, single output system. Test system 2 is having the characteristics of time delay. This is a time delay system that we have taken up. The third system that we had considered is a fractional order system. This is another challenging system to reduce. And fourth one is a multi-input, multi-output systems. So these are the 4 test systems that we have considered, and you may find that these are some of the results that I have shown of the reduced order model in the delta domain as well as in the continuous time domain. And if you look closely observe the results, you will find that the coefficients are pretty similar. The coefficients of the delta domain approach and the continuous time domain approach are pretty similar, justifying the unification of the discrete approach with that of the continuous time system at high sampling frequency. So this is an interesting feature of the delta transform or the delta operator that we deal with. So these are some of the results that we have shown for the test system 1, 2, and 3. Fourth is in the next slide, I suppose. Yes, this is the result for the test system of the multivariable system or the multi-input, multi-output system as well. So going ahead, if you discuss the time and the frequency response matching, we are almost at a close, excepting the part that at higher frequencies we find that the Bode plot, they are mismatched. They are producing some mismatch in a few of the test systems, which indicates that we need to take some countermeasure to preserve or maybe some constraint violation took place in the frequency parameters. Now discussing the last application of today's lecture, we will discuss about the controller design. Usually we have the controller design being achieved using a reference model, and that may be matched either exactly or approximately So we have two types of reference model matching. One is the exact model matching, and the other is the uh, uh, approximate model matching. However, your exact model matching is not guaranteeing you the corresponding hardware implementation. So often it is being discarded, and we go in for the approximate model matching technique, which is an alternative. It is a good alternative in which the reduced models which we have developed earlier can further be applied for its controller design. And these are some of the steps. This is the general form of the controller which we have represented, and we have chosen a reference model corresponding to this controller, or corresponding to the transfer function we have that satisfies some desired specifications. The desired specifications are being kept fixed for our case, and we have gone for a unity feedback output response and comparing it with the reference model response, and we have computed the integral of square error in this case, and in order to find out the difference between the model output or the reference model output and the corresponding closed loop response of the plant, including the controller. And the controller is having some unknown parameters which we have estimated using this metaheuristic technique. So these are some of the results of the test system. One means this is a CISO system controller that we have devised, and these are the KP, KI, and KD values. These are the tuned values for the controllers corresponding to the model matching. We may see that the step response of the reference model is almost replicating the closed loop response as well. And also the errors that we find, they are very close to zero as well. These are some of the results for this time delay system, I suppose. Yes, it's for the time delay system that we are referring, and out of which we are also finding that the response are almost matching. This is a response for this test system 3. That means fractional order system for which the controller is being designed. KP, KI, and KD values are being evaluated, and we get the J-mean, or the minimum value for the error, as 0.3377 in all of these hybrid combinations. And finally, if we look at the MIMO system, I'll be having 4 outputs: G11, G12, G21, and G22. So there will be four corresponding transfer functions that we have found out, and we find that the reference model is closely resembling your closed loop response once the controller parameters are being found out. Coming to my last slide, this is the last slide that we would like to highlight upon. There are a few publications from already on this. These are some of my latest publications, although the first 4 belong to my BTech student Abhimanyu. Mostly it is his solo effort almost in getting these papers being published. And after that, fifth one is a publication which we have discussed in this particular slide ahead, with system identification methods using unified approach. And another is a model order reduction. This is consisting of the CISO system, and fingers crossed for the multi-input, multi-output system, and time delay system, and fractional order system. They are all under review as of now, and we are expecting by the end of this year, we are expecting some good results for that. So this is all from my side. Let me stop sharing. I am done with it. Let me take some